Okay, can we start?
Yes, ma'am.
So, good afternoon, everyone. So, I'd like to present our research part of very briefly our research that is happening at IT Indore, and myself, Dr. Neelima, and this is being work carried out by my PhD student, Meghna Sharma. So, this topic is on advances in ground improvement. Basically, in the conventional ground improvement techniques, we use a lot of materials like cement and stone, etc., which is not sustainable. So, we would like to work on some sustainable methods using bio approaches, and so the talk is on biomineralization for granular soils. So especially looking at the geotechnical challenges, one of the major thing that we face is like instability issues because of seismic activity, especially in terms of liquefaction or lateral spreading, which we have seen in the previous classic events of earthquakes, especially Niigata earthquake, Alaskan earthquake, and Tohoku earthquake also, and even our Indian Buzz earthquake as well. So what happens is like the soil behaves for a specific time. The soil taking the load and behave like a viscous fluid. So this is what is called a liquefaction hazard. Let's see the right hand side some of the pictures because of the liquefaction hazard. You can see here it's very dramatic pictures and adjacent structures, and this is very site specific. So what we are trying to do is like how to do the ground improvement for liquefaction, increasing the liquefaction resistance through bio approach. That is the overview of my topic. So for the soil liquefaction, especially when the shear strength is very less, like if the pore pressure shoot up and shear strength is reduced, and then the soil will fail and it behaves it stop taking the load completely for some time, and then and slowly after the event or the seismic event, it starts gaining the load, taking the load. So, but during that period, the structures may collapse like this. So there is upward water pressure, that is gradient, maybe effective stresses become zero, and because of seismic event, or it behaves like a fluid, as I mentioned. So these are some of the events in Taiwan earthquake in 2018. See the structure, there you don't see any kind of fine crack also in the superstructure, but the structures is completely collapsed. So this is another during the Niigata earthquake. The other view of this picture is on the Kramer textbook as well. So soil improvement techniques in the conventional way, we do have jet grouting, soil reinforcement, compaction methods, dynamic compaction, or using some geosynthetics or geogrids, whatever it is. So, but they are like carbon intensive or like uneconomic methods because they're very costly and not environmentally friendly. So what we are trying to do is like in this one, we want to approach something like in advanced methods, people are going alternate or waste materials or industrial waste people are trying to use. So in bio approaches, like we do have biopolymers, use of biopolymers like gum or like agar gum, etc., and biochar also, which is one of the upcoming areas where we can reduce the agriculture waste and use of biochar material for stabilization. And then nanomaterials also people are working on that, but the problem that is associated is in the large scale field application to apply in the real field is a very major challenging. So what we are trying to do here is like if you look at the nature's perspective, nature, in the nature we can see this is actually it one of the national park. You can see that is biological biochemically induced because of wind erosion, this kind of spikes you can see, but there is a kind of calcium formation that happened along the desert soil, and it made like a kind of rock. And this is, you can see here, stromatolites are, they are formed along the beach. Okay, so this has been because of the action of cyanobacteria. So nature itself has this kind of processes which we can capture it and apply in our engineering problems, so that we can achieve some kind of sustainability. So biogeotechnical methods are very upcoming now, and for ground improvement it is a highly multidisciplinary because it needs a lot of inputs from biology, chemistry, and engineering, etc. So what we do is like soil has some sort of bacteria in it, non-pathogenic bacteria. So we would like to increase the activity of this bacteria so that calcium carbonate can be formed, and it can bridge the gap between the grain to grain, because in soil the load transfer mechanism happen because of the contact mechanics. So if you can increase the number of contacts with other grains, then obviously the shear strength can increase. So urease producing bacteria and denitrificating bacteria are required for this kind of approaches. In this also there are different methods of biometric methods. One is like MACPE, which we are working on at present now, and microbially induced calcite precipitation, EACP enzymatically induced calcite, and MADP where it is like desaturation happens. And so these are the broadly three different classifications. I'll just give you an overview of it, and anybody interested, please write to us. So we'll be very happy to have any sort of collaboration or for any kind of internships as well. So in the MACP approach, there are two ways. Like either it can be done through biostimulation or by augmentation method. In stimulation, what we have to do is like so we native bacteria, and in augmentation we introduction of a specific species, we do it. Okay, so and we use reagent solutions like urea, calcium chloride, and nutrient broth we'll be providing it. And then the calcite crystals will be formed in between the grains, so that the voids between the grains can be closed, and the shear strength characteristics will be improved. And in the recent years, a lot of significance on this biological process of the soil has been identified, and the process of biomineralization has emerged as one of the very new technique, and it's a sustainable solution. And this can also can be applied in the field, which we are also trying to explore it at present. And because of the time constraint, this is a short presentation, I'm not going to put it up. And this biogeochemical process, this is actually the overview of the entire process. Okay, where Uras process happens and the calcium carbonate crystals will be formed. Okay, and see, when the sand is like that, it has a kind of flow kind of characteristics, but when a treated sand, it becomes like a rock. Okay, so this is our samples from our lab. So we also done some kind of micro analysis like SEM analysis, XRD analysis. And so the key attributes that comes is like control and regulation of biology under the chemistry, which can accelerate or delay this complete biogeochemical process. And this can be monitored, process can be monitored, so that what we can find it out is like with the different kinds of the days of treatment and amount of treatment, we can see what is the percentage of treatment that can be achieved. And field application, yes, some research is going on in different parts of the country, or sorry, in different parts of the world on this particular problem. And in this biomeditative soil improvement, actually there can be three different ways. One is like mineralization, which we are working at present, where there is a calcium carbonate crystals form the voids, and biofilms along the grains, on the surface of the grains, or biogas generation. So there any three can happen. So we are targeting only the process which can give us biomineralization. And the treatment, like which one suits well, depends upon the kind of soil. We have taken the Narmada sand because it's a granular material. So at present we are working on the river sand. And so hydrolysis hydrolyzed urea concentration as a function of the time. So we also studied that, because this is some of the factors, especially pH, the change in the pH, because as the process is treatment process goes on, there is a change in the pH because the calcium carbonate is forming, and urea concentration and electrical conductivity also will be various. So that can be monitored. So we also developed a small numerical model for monitoring these parameters. And in the microstructure, if you see here, as I said, like there may be bonding between the particles. This is the calcium carbonate that got binded. You can see in the CM images also white color things, and which can increase the angularity of this particles. As the angularity increases, obviously shear strength is increases. So some more SEM images from our study, you can see here calcium carbonate crystals was formed here, and here also the white color patches here also, maybe in the bed also. So, and microbe beds have been observed, calcium crystals again. See this microbe beds. Okay. So, and we have used three different kinds of bacteria. So for all the three, we were trying to see which is more effective. And the first application I would like to present here is like this method for liquefaction mitigation of the sand. And the Narmada sand, which we are available in this region, the Madhya Pradesh, so extensively, is a liquefaction susceptible sand. So then we try to use that particular sand, so that the treated test has been carried out. So we also had done different kinds of tests, like in the lab, like UCS, to find out the shear characteristics, friction angle, pore pressure response. And we also try to see what is the effect of freeze and thaw on these treated samples. And we have try to use different kinds of samples for direct shear, U-shears, and track shell also we have carried out. So coming to the classification, the sand was behaving like a rock sample after its treatment that I have shown you even in the image, and there is a reduction in the strength less than 5% and 10% of different freeze and thaw cycles in the treated samples, which is okay, well within the values. And the shear velocity showed a minimum precipitation of 3.25 calcite. The samples are liquefaction resistance even after 20 freeze and thaw cycles, which is a very, very good improvement. So similarly, UPV and shear modulus values have also been for the treated samples were almost like a sandstone material. So, and there are different applications of MICP, not only for the liquefaction is just one part, for oil recovery, enhancement of the recovery, reclamation of old structures, and like if there is any crack in the structures, like, some kind of stone column or something in temples or something, that can be, this method can be applied there also. And even for rock failures, rock fractures, for reducing of the permeability, and, as I said, liquefaction and landslide issues. So contamination, immobilization, which we are also having a paper on this particular part, erosion control, improving the bearing capacity for the foundation design, etc. So these are the different applications we have in MICP technique. And so this is one of the very sustainable and very interesting approach where we can use the natural process and activate that, so that our engineering problems can be solved. So it's very, very cost effective and environment friendly. Thank you so much.